In this question, we are asked to find the angle between the minute hand and the second hand at 2:16. To begin with, I want to consider how many degrees it takes to go around the entire circle. Well, I know that's going to be 360 degrees, and also to go all the way around the circle or all the way around the clock is going to be 60 minutes. If I look at numerator to denominator, I can divide them both by 60 to simplify this to mean that every 1 minute on the clock is rotating by 6 degrees. So when we're looking at the clock and the minute hand is at 16, we have 16 minutes. So if I multiply the numerator by 16, that would give us 16 minutes. Multiply the denominator by 16, that gives us 96 degrees. In other words, starting from straight up vertical, if this is 0 degrees, it's rotated around by 96 degrees with the minute hand. So that is half of our problem. And then I'll minimize this to create a little more space. Next, let's look at the hour hand, and this one takes a little bit more work. In 1 hour, the hour hand moves from the 2 to the 3. In other words, that's 5 little marks in here, which would make that 30 degrees. So what I know for the hour hand then is that 60 minutes isn't equal to the entire 360 degrees, it's only equal to 30 degrees. Now if we simplify this, multiplying numerator and denominator both by 30, we would get that 2 minutes is equal to 1 degrees for the hour hand. We want to see how far does the hour hand move in 16 minutes. So if we multiply the numerator by 8, that would turn the numerator into 16 minutes. Multiply the denominator by 8, and that's 8 degrees. So what I know then is that from the hour hand, going from straight vertical at 0 degrees, is rotating by 30 degrees to get here, another 30 degrees or 60 degrees to get to the 2, plus another 8 degrees. So then this angle is 68 degrees. This whole thing is 96. This part is 68. We want to find this angle in between that I'm coloring in yellow. So if we took 96 minus 68, we would get 28 degrees between the minute hand and the second hand at 2:16. In problem number 12, we're trying to find the area of this isosceles trapezoid. Maybe you don't know how to calculate the area of an isosceles trapezoid, or maybe you're thinking with these values you don't have enough information. But consider this. What if we chopped off this triangle over here on the left, this is what I have diagrammed over here, this shaded rectangle, we rotated it around, reflected it, and moved it over here. In other words, I'm taking this triangle and pasting it onto the side over here on the right, and then we would have this shape. So again, we've chopped it off of the left, we've moved it over here, now we have this. It's going to line up perfectly since this length is congruent to that length, this side is congruent to that side because of all the symmetry. We have created a rectangle. And the area of this rectangle is length times width, or base times height. So the area of this rectangle, which is exactly the same thing as the area of this isosceles trapezoid, is x times y. So imagine that this had a spinner on it, and we spun it around, and it was going to land randomly somewhere here. Each location is equally likely because the central angles are all 90 degrees. All 4 of these regions are the same size. But we want the expected output to be 2. Sometimes it'll land on +1, sometimes +3, sometimes +5, and sometimes the x. And if we did this 100 times, we'd want the average number to come out when we added them all together, divide by 100. We want the average to come out to 2. To figure this one out, we have to realize that 1/4 of the region is with the +3. So we're weighting each one of these sections. We have 1/4 of 5, 1/4 of 1, plus 1/4 of x, and all of those together we want to come out to equal 2. I don't like the fact that everything here is times 1/4, so if we multiply all 5 of these terms by 4, we'll just get rid of all those fractions. 3 plus 5 plus 1 plus x equals 8. 9 plus x equals 8, so x equals -1. And the reason why I used that strategy in the previous example is because in this one we're going to use that exact same kind of strategy. Each of these regions are different sizes. For example, you're more likely to land in the region with 90 degrees, or it looks like this one, as opposed to just the mere 30 degrees or only 50 degrees. So to take that weighting into consideration, I have each one of these regions with the value associated with them multiplied by the central angle over 360 to tell us what fraction of the entire circle that we're dealing with. The only one that I don't know is this y. I do know that there are 360 degrees in a circle, and if all of these angles are added up, that's 250, which leaves 110 degrees left for the y. Like the previous example, I don't really want to work with fractions if I don't have to, so we're going to multiply all of these terms by 360. In other words, we're getting rid of all of these denominators, multiply by 360 times 360, and the right side is the only one that really changes with the numerator at least. And now we're just going to multiply all these numbers out. 90 times 6 is 540. 80 times negative 3 is negative 240. 30 times 7 is 210. 50 times 4 is 200. Plus 110y is equal to negative 360. In the next step, I combine all the like terms on the left-hand side to come up with this equation. And then if we subtract 710 from both sides, we get 110y is equal to negative 1070. Divide both sides by 110, and that would give us that y is equal to negative 107 over 11. As a decimal, it was negative 9.72 repeating, but here is an exact value. So while it's not exactly a pleasant number, y would have to be equal to this so that the expected output would be equal to negative 1. In this last one, we're supposed to solve for x in order to make this equation work. Now, if I tried to do it just straight algebraically, I would square both sides. Squaring the right is just 225. But when we square the left, we can't just square the first term and square the second term and then call it x plus 15 plus x. Because really, we'd have to be squaring this binomial, which means we'd multiply this times itself, and we get some kind of ugly terms in there. So rather than doing that, I'm going to just do a little bit of trial and error, actually. I know that if I plug x equals 1 in, that both of these would come out to perfect squares. So if I plug in 1 plus 15 is 16, the square root of 16 is 4, the square root of 1 is 1, but 4 plus 1 definitely does not equal 15, so 1 is too small. And if I start looking at consecutive perfect squares, I can start to see how they're different. What I mean by that is, I want two perfect squares that are different by 15. And that would make my x value then equal to 49. Just a little bit of trial and error. I could go through a bunch of them, and I'm really fast forwarding here. If I plug 49 in for x, that's 49 plus 15 plus 49. Is that equal to 15? Well, 49 plus 15 is 64. The square root of 64 is 8. The square root of 49 is 7. 8 plus 7, yes, that equals 15. So x is equal to 49. Certainly other ways to do that one, but trial and error is really the way that I would see to approach that one.